again, thanks everyone for coming to this talk. Today, I'll be talking about a self-distillation method, which is a recently popularized technique in deep learning. And I'll provide some analysis because it kind of looks like a black box, and the that we get out of it is not clear why we get those. So I try to answer some of the questions around self-distillation. By the way, I forgot to correct the date. I apologize about that. So this is joint work with Mehrdad Farashsavar from DeepMind and Peter Bartlett from Berkeley and Google. Okay, so first I should say that I will try to keep this talk high level. A lot of the details I'll skip because I want to keep it high level. But if anybody is interested in more details, you can look it up. It's on archive, and you will find all the proofs and details in there. All right, so let's start with the definition of self-distillation. Suppose you have some training data. It's a supervised setting, so my training data consists of pairs like x0, y0, a set of these points, and then I feed those into a architecture and a learning algorithm. So at the end, is a function for me, which I show as f0. This function makes predictions on inputs now. Well, if we train this model well, these predictions will be close to y0, right? If I provide x0, the produced prediction will be close to y0. But it's not necessarily identical to the ground truth labels. So there is a slight discrepancy, which can come from, regularizations in your learning scheme, implicit or explicit. Very close to y0, but it's not the same. Because of this small difference, if I treat these predictions f0 as new target labels and retrain my model with that, retrain my architecture with that. So inputs are still the same, but instead of ground truth label, I use the predictions I already obtained from a trained model. And then retrain another model from scratch using this pair, x0 and y1. I get another model, f1, which is now different from f0. And I can keep repeating this loop. I get f2, f3, and so on. This is called self-distillation. And one interesting observation people have had is that sometimes these intermediate models, let's say f2 or f3, have a better test performance compared to the original model f0. And this is a little bit surprising because everything here is the same. So this is the same architecture that's being repeated. It's the same training we're using, and it's the same data set, except that we are tweaking the labels by using previous round of predictions. But still, there is no external information coming from anywhere. So everything is just coming out of this original data. Just because of this loop, we keep modifying the labels. So it's been observed that it can improve, but it's been surprising. So my study was to understand what's happening here. And when I wanted to study the underlying phenomenon that helps to boost the test performance is more profound. It's not restricted to deep learning scenarios. Even if you consider a very simple regression task. So here you can see a bunch of points, the blue dots, and a ground truth curve, which is shown as blue curve. So suppose I don't know the blue curve, but I only see these sample points, and my goal is to estimate these points, right? But I observation. So these, let's say the underlying curve is the orange one, like the clean curve. But actually, let's go with colors like this. So the actual curve is orange curve, but I don't see the orange curve. So I only see a subset of samples shown as blue dots. but these dots are noisy observations. In practice, we have noise coming from various sources, right? So if I just go and try to fit a curve to this point, I get the blue curve. Bumps and less smooth than the original curve, right? But if you do self-distillation, even in this simple setting, which I'll elaborate a little bit later in this talk, you can actually get something close to orange curve. And again, the point of this slide is to emphasize that if you perform this self-distillation loop, even in this simple regression where we use L2 loss and let's say a polynomial here to fit, you still observe the same phenomenon. So let's start the analysis by first setting up the problem. The analysis will not be about deep learning because that's too complicated. Instead, I present the analysis for a more simplified setup, but the kind of conclusions we make here, we will empirically see that they agree with what we see in deep learning scenario as well. This framework, simplified framework, helps us to go deeper and do some analysis instead. We are looking at a regression problem. So we have a bunch of training points, xk, yk. Yk is, let's say, it's a scalar. Xk is a vector. And there's an underlying function. And there is a function that we are trying to basically estimate, which I show as f. So the goal is to make the predictions of f for xk to be as close as possible to yk. So here, for simplicity, we are penalizing the L2 loss, or here, instead of penalizing, I'm putting a tolerance. For individual points, I have this squared difference as my error, and then I average it across all my training points. So the average is like what I want to be small, and therefore I have this inequality that requires the average error to be less than epsilon. Okay, is this enough? Well, if I'm looking in the space of all functions that can meet this criterion, there are infinitely many functions that can do this, right? In fact, there are infinitely many functions that can even attain zero. So this is not enough, because I could have very weird functions, very, I don't know, bumpy functions that can fit these points, but they will not have a good generalization. So what I need to do to make this problem well posed and say what kind of solutions I prefer among all solutions that meet this error criterion is to add a regularization criterion here, which I show as RF. So R is called a functional. It returns a scalar. And the value of this scalar is something like a penalty, how much I like this f in general without even seeing the data. So, for example, R could prefer smoother functions. So the rougher the function is, R can provide a larger penalty, a larger value. So now combination of this minimization with that error tolerance makes sense, right? Among all functions that meet this error criterion, we prefer the one that have, I don't know, maybe the smoothest. And then, of course, there are many ways that you can express this form of R, regularization R. Here we are considering a specific form, which is shown on this slide. So it's written as a double integral. The function that you provide as input, as I said, is f, and you have another function which is called u in this slide, and that is called basically the regularization kernel. So u determines how, right? Don't worry about the details. I'll provide some intuition about what this kind of R does. For now, just think of it as some like mathematical form. The exact form of it is not relevant for now. We'll get back to this. All right. With this setup, though, with this specific definition of R and L2 loss, now the problem is well posed. And more importantly, we can provide some analysis on self-distillation. So let's the very first thing we want to know is, okay, what is the form of the solution for this regularized regression problem? Actually, this form of problem has been studied extensively in the literature, and there is no novelty up to this point from my slides. Actually, if you look papers in the 90s, for example, written by Poggio and Girossi, they have a series of interesting papers that tackle this form of problem. And in this slide is that I moved the constraint, which was the error tolerance, to the objective. And you can always do that using Lagrange multiplier, which is a method in optimization. So you can convert a constrained optimization to an unconstrained optimization. So that's straightforward. But once you write it in this unconstrained form, then it's a standard. And as I said, the form of the solution is known and can be written in closed form, which I'll show in a second. So in order to understand now the solution and also how the self-distillation works and all that, I need to provide some quick introduction to the notion of eigenfunctions in case people in the audience are not familiar with this. So I hope people have heard about eigenvalues and eigenvectors. So first, maybe remind you the definition of that. So given a matrix, given a symmetric matrix, if you multiply that matrix by a vector v, and in return it becomes equal to a scalar like lambda times v, then we call that v an eigenvector of this matrix, and lambda to be an eigenvalue of this matrix. Now, eigenfunctions is generalization of this to functions. So instead of like vectors and matrices, we are now thinking about functions and operators. So here, for a function like u, which is actually it's to be more precise in language, it's a kernel. So it's a function u and associated with this integral operator. If you apply that to a function like phi, then if I get the phi again times a scalar, then I call phi to be an eigenfunction of this linear operator whose kernel is u, and lambda to be its eigenvalue. In the same way that by a weighted sum of its eigenvectors, you can represent functions with the weighted sum of their eigenfunctions. So eigenfunctions come from this linear operator associated with this kernel whose kernel is u, and these can give me something called complete basis. These eigenfunctions can give me a complete basis, which means that by linear combination of these eigenfunctions, I can build any functions in that space. Space is complete. Assuming that these eigenfunctions give you a complete space, then what I do is I represent my prediction functions, the unknown functions, using these spaces. And basically, by changing the coefficients ai, I can build different functions, right? So instead of now saying, okay, I want to find a function f, my goal is to find the coefficients of these bases, ais, right? Because the phi is already given by the regularization. Regularization operator has nothing to do with your training data. It's just penalizing, different functions based on their roughness and smoothness. So I can rewrite the problem using this expression for f, right? So let's just replace the definition of f with this basis expansion. So that's you see in the bottom. Now, why this is useful? Because now the regularization term becomes sum of squared of the coefficients ais, except that each coefficient is also multiplied by lambda I, which is the eigenvalue associated with that basis. Okay. By the way, Rahim, I don't know if like we want audience to ask questions while I'm giving the talk, or it's more at the end. Can you advise me on that?
Yeah, whatever you want, we can do.
Yeah,
both.
I think because I don't know what is the background of so, but I don't see your screen where people post questions. So if there's any question, please let me know.
A question, if you don't mind.
You do have a question? Sure.
Yes. So this
Okay.
the improved test performance of self-distillation, that reminds me of the effect of over-parameterization in neural networks. Is that right?
Okay, what happens is that both over-parameterization and self-distillation induce some regularization and different types of regularization. But the reason that you see a boost in test performance from either of these is because of the help they get from the underlying regularization. So over-parameterization, loosely speaking, encourages something like low-rank solutions in the weight space, while in self-distillation, it prefers in the eigenbases of the kernel. So both of them have to do with low rank and sparsity, but in different different types of sparsity. So like different spaces. But other than that, they are not related because they are two different regularizations.
Okay, thanks.
No problem. Okay, so is there any question from audience?
No, not yet. So if you don't mind, I will interrupt you maybe every couple of slides if there is any question.
Okay, so far we just reduced, this variational problem to something that doesn't have any integral. We move from integrals to sums by the virtue of the eigenfunctions. All right. So to gain again some intuitions about this, let's look at the toy example first. Suppose I'm looking at functions that are defined in the interval of 0 to 1. So functions that map this interval to real numbers. As follows. I can say, okay, I prefer smoother f's. So I'll penalize the second derivative of f, right? Because the derivative is like, if you have bumps, the derivatives have need to, okay, maybe it's easier to say this way. If you have flat functions, then the derivative is 0. If you have a straight line, the first derivative is 0. If you have just a quadratic, which is like a unimodal curve, sorry, if you have a flat line, then the first derivative is 0. And if you just have a line, not necessarily flat, then the second order derivative is 0. And this way you can pick any order of the derivative, but it penalizes some notion of smoothness, right? So here I'm just picking the second order derivative, for example. So any flat line, I mean constant function, as well as any linear functions, gives you 0 here. So this lines and constant functions. Okay, so I want this function to be smooth over the entire interval. So what I do is I square this penalty, because I don't want positive negative to cancel, and then I integrate it over this interval, right? So this gives me the regularization operator. Now from this regularization operator, I can obtain the eigenfunctions and eigenvalues. And the way I derive those is beyond the scope of this talk, and it's even not necessary. That, okay, if I penalize the second order derivative, then what these eigenfunctions look like. So at the bottom, you see the visualization of this. On the left, you see the eigenfunctions, and on the right, you see the eigenvalues. The lowest eigenvalue comes from the blue curve, which is like actually this curve on the left looks like sinusoid with increasing frequency, right? So you can see as we go from blue to red, red having the largest amount of penalty, you are actually smoother function to things that have higher and higher frequency, right? So essentially, this is saying that if I would like to reconstruct my function using these basis functions on the left, I can use any of those. But if I want to use, for example, the red one, I have to pay a higher cost for using that, for that to contribute to my solution than the blue one. So through this lens of eigenfunctions, you can see exactly, okay, what basis functions are being used and how they are penalized. So it's just for you to have an intuition in this regularization framework. All right. What I told you was that earlier that, okay, this kind of regression problem and regularization framework has a closed form solution. Already known. I mentioned even some papers from the 90s in the machine learning literature. There's nothing new about the form of this solution, but we need to use this form of solution for our analysis. So I'll just show you what is the form of the solution. But before being able to definition, one more mathematical definition, and that's called the Green's function. So it's a simple definition. So given a regularization operator whose kernel is U, so I have, this is basically what I was using earlier in my slides. Actually, oh, you see it even on the top. So this is the kernel of the regularization. So if I can find a function G that satisfies this identity, so essentially multiplying that with my kernel and integrating gives me the delta function, then that, if I know the Green's function of my regularization, then I can use that, I can evaluate that at my training points in order to construct a matrix G. So this matrix G has a components, like the JK component of this matrix is application of Green's function to training points xj and xk. Green's function has two arguments, in the same way that our regularization operator has two arguments. So this matrix G is shown by capital G. I can also, and that is by evaluating my training points only at one of the arguments. The other argument here, the first argument, is just free. So it's still a variable. As a result of that, I get a vector, but this vector, each component is a function of x. Okay. So once I construct this small g and capital G, then I can express the solution to this optimization problem as below. So here f star will be of this form. So the training labels, if you remember in this setting, my training labels were scalar. So if I stack them up as a long vector, I'll get a vector y. So this is the vector of all training labels. And as I said, this matrix G and small g, vector G, also are constructed from all training points, right? Either as pairs or just one training. So here, all the training information is encoded, right? And by applying this, by solving this, I obtain the x right now. So any unseen x, I plug in here. The only place that it affects is this small g, right? Because that's the only place that it depends on x. And the rest is from my train. So this part is from training data, and this part is completely from regularization. Okay. All right. So if there's no question up to this point, as I said, this is a known result. Now we have all the preliminary results that we need for doing an analysis. One last thing before I start the analysis, maybe making some important connections. So one thing is that if you are familiar with kernel ridge regression, which essentially means you do kernel regression with L2 regularization, then you will recognize that the form of solution that we have here is exactly the same as what you would get in ridge regression. So this means that this kind of like variational optimization integrals and derivatives, this kind of variational optimization is equivalent to a kernel regression, ridge kernel regression task, right? Both of them boil down to having the same solution. And why is this important? Because now this is kind of the argument that we can use to relate these results to neural networks. So if you have heard about neural tangent kernel, which is a new notion in relatively new notion in neural network literature, it tells network becomes wider and wider, then this neural network, although it's highly nonlinear, like at the limit, like when the width goes to infinity, this network behaves like training these networks is the same as just doing a ridge regression, ridge kernel regression. And the kernel is like depends on the architecture, activations, and all that you use. But at the end, it like there will be an equivalent kernel for this. When you're training it, it's just doing a kernel regression if you're doing regression. So this is important because it tells us, okay, some of these analysis that actually, if you believe the NTK regime and results, then this means that our results are immediately applicable to wide neural networks. But this is just a connection. We don't want to get into details of that. We will continue with the simple regularization. All right. So now I think we have everything we need in order to start our analysis to now ask the question, okay, what happens when we do self-distillation? And hopefully this will tell us why we get better test performance after multiple rounds of self-distillation. All right, a little bit notation. As I said earlier, this y is the vector of all ground truth labels, which I stacked y1 all the way to yk. And I can do the same thing with my predictions. Again, my predictions are scalar. The predictions from all the training points I have into another vector. So here, capital K is the number of training points. And I just showed that if we are solving this kind of regularized regression problem, then F has this form. So you can obtain F if you know Y by evaluating. By the way, the small g disappeared, and we have capital G because this is evaluation of F at the training point. So if I have that small g and I evaluate that at my training point, matrix G, maybe it's worth going back. So, okay, so this is my small g. Now I can evaluate this at, let's say, point x1. So if I evaluate at x1, I get a vector. If I evaluate at the x2, I get another vector, right? So if I put these vectors together, I get a matrix, which is this capital G. So that's how the capital G shows up. So the evaluation of my predictions at my training points will have this form, right? All right, now because we want to iterate the training process, it's better to index them by the iteration round. So let's say it's denoted by F0, right? So the initial labels, which are ground truth, are y0, and the first prediction function that I get is F0. By the way, one thing that I didn't mention was this regularization coefficient C. So maybe I quickly go back to tell you where it came from. So remember, this was the kind of setup that we had, right? So we were trying to meet a criterion on the training error. We wanted to minimize the regularization form, right? So as I said, we can convert this constraint form into an unconstrained form using Lagrange multiplier technique. So that way, we will now have to deal with an extra coefficient, which is called the Lagrange multiplier. So the C is coming from there when we move from the unconstrained to constrained problem. All right. So this C could change in each round. That's why I also have C index. So, and when I go to the next problem, it could be a different value. So that's why it's C0, C1, and so on. All right, so initially we have this. Now, what do we do when we want to self-distillation? As I said, we now replace the ground truth labels with predicted labels. So I go to my second round, which now I show here as Y1. So I set my target values to be F0 and then solve the same optimization problem. Every is instead of Y0, I'm replacing Y0 with Y1, right? And Y1, I already have the form of the solution from here, right? So I plug it in here and I get this one, right? So this is my updated model, right? And I can just keep repeating this. So in general, after like T rounds of doing this, I can express the form of the solution as something like this. So it depends on the initial ground truth labels like this. Matrix multiplication going on in the middle, and here I have the vector G, right? So whatever is that's happening should be here in this multiplication, right? Because if you compare this with your initial solution, G, the vector G is the same, so there is nothing happening here. The ground truth labels are the same. The only thing that is different is, okay, I'm going from like this form to this form is now a product, right? So whatever's happening, the interesting stuff is here. All right. For the sake of this presentation, in order to simplify the results, I'm going to make a simplifying assumption just for the presentation. It's not required. And that is to assume that these C's are not changing over iterations. So instead of having C0, C1, so on, I'll just have one C, okay, for all iterations, which is written here. If you would like to see the full analysis without this C being constant, it's available in the paper, but it makes the and again, for the sake of this presentation, I want to make this simplifying assumption. It greatly simplifies and gives us very clean results, but it still maintains the points that we want to make about self-distillation. It still is able to show the kind of regularization effects that we get from self-distillation. So with that note, I'll just replace all CIs with a constant C. Now, if I do that, things become much nicer. So remember, the form of the solution was locked. And now if all these C's are the same, I can just raise this thing to power of T. This doesn't change anything. Also, one quick thing to like some notation thing is that the matrix G can be decomposed using eigen decomposition. That's what I'm doing here. So you can write G as its eigenvectors times a diagonal matrix, and again, its eigenvector transpose, right? So the matrix that contains by V is the matrix, the diagonal matrix is shown by D. So I can always write G in this form, right? But it greatly simplifies the analysis that I want to do here. So if I add a multiple of identity to any matrix, it doesn't affect the eigenvectors of that matrix. Also, if I multiply these matrices, also if I invert the matrix, it again only affects the eigenvalues, and so on. So what happens is that I can just push these eigenvectors to the sides and only keep the diagonals of G, diagonals of this eigen decomposition in the middle. So that's what I'm doing here. Again, you do this because it makes things easier and clearer. So if T goes to infinity, if T is super large, then let's see what happens. So as I increase T, okay, so maybe here all the elements of these diagonals will be less than 1. Why? Because I'm multiplying d times something that is d plus a positive number. So you think of it as a scalar for now. So it's like d divided by c plus d, right? So always the denominator is greater than the numerator. So this is a less than 1 number. So if I raise this to a large power, then it always like becomes smaller and smaller. But shrink faster than others. Specifically, if I have values that are close to 1, if I raise them to a power t, they shrink much slower. In fact, if you just choose 1, it doesn't shrink at all. So you can raise 1 to any power and still 1, right? But as you reduce this number, so if the original d's have sorry, not original d's, but the original ratio has a number that is smaller, then when you raise it to power t, it shrinks much more. It means that there'll be a race between these diagonals. And if I raise them to a large power, only the largest the largest element will survive, because the rest will shrink much, much faster relative to that guy. So to the point that they kind of look negligible with respect to that. So this is like if I take t to infinity, then the only thing that matters will be the dominant value on this diagonal. Everything else I can ignore because they become like extreme this single value. So what is happening here? We are actually making this diagonal matrix very sparse, right? Because again, as I said, everything except the largest value will behave like nothing, like 0. So in that case, starting from some dense matrix D, after raising it to a large power t, it behaves like a sparse matrix where only the largest value has survived, right? But that's when t goes to infinity. Matters. But if you put like intermediate values of t, it kind of looks like it's progressively sparsifying this matrix D. As I increase the value of d, it becomes more aggressive in killing the smaller diagonals, right? So I start from like the original values. It's not immediately like a rank 1 matrix that has only like a 1 non-zero eigenvalue. As I increase the t, it rank. So the smaller ones diminish fast. So I'll show this within a toy example in a second. But basically, this is showing what's happening in self-distillation. So it says that, okay, if I have a regularization operator, it gives me this matrix G, right? If I evaluate it at my training points. This matrix G has some eigen decomposition. And when I do self-distillation, it's sparsifying the diagonal matrix used in between. So it says that and smaller number of basis vectors in V, right? And that way we are limiting the capacity of the representation. We are limiting the capacity of how this F can fit the training data. And that's our regularization. Regularization is just a way to limit the capacity of the space of models, so you cannot easily fit arbitrary training data. Like continuously removing more and more eigen vectors of this matrix V. Okay. So I already explained the capacity control, but maybe here it's slightly more clear what's happening. So this is the ground truth labels y0, right? And V is just the matrix of eigenvectors, which is a rotation matrix. So if I apply V to my y0, the only place that depends on training points is I'm sorry, on the training labels is now this Z0. Like everything else here doesn't see the labels, right? So this is saying that if I rotate my labels by this rotation matrix, in this rotated space, I would like to use a sparse number of labels in order to fit my function, right? Because as I said, when t becomes larger and larger, it kind of shrinks more and more eigenvalues on this matrix. So it uses fewer and fewer components of this Z0. So the only thing to make sure you understand is that this 0 is not the original label. It's not saying that I want to choose a subset of like original labels. It first rotates these labels, and then in that rotated space, it's using a subset. So, but still, it's something that is limiting the capacity of this representation, right? Instead of using the full information in Z0, I'm now using this. In fact, you can develop a formal generalization bound using this, but in the interest of time, I'll skip the details of that. I'll skip the details of that to show you some experiments as well. But these details are available in the paper. All right, so let's get back to our friend, which was this function we had earlier, and this regularization where we were penalizing the second derivative, right? For this example, I can add Green's function, but in order to use this result for self-distillation, you don't need to have the Green's function. This is just for the completeness of the presentation. And you even don't need to worry about the form of this Green's function. But just to say that for this second order derivative thing, we can build the Green's function as shown here. And okay, now let's look at these curves. So this plot is the Green's function itself, right? It had two arguments, so it's a two-dimensional curve. It's like a bump. I showed early in the talk for, like I said, okay, the underlying curve is this orange curve, but I only see noisy subset of samples from it. And if I just fit, fit to this data, a curve, I'll get this blue curve, right? Which is far from this orange curve, right? So here, this is showing how it behaves if I do multiple rounds of this self-distillation. So the blue curve is what I obtain this optimization problem, right? So if I just use this regularization, L2 loss, and just the closed form solution that I showed earlier, if you just build the prediction function f, you will get this blue curve. But now, if you evaluate this blue curve at these points, these coordinates that I have my trained data, so only the y component is now changing. The x component is the same. Here is actually, I think, uniform, if I'm not mistaken. But we again reevaluate the function at this point, and this time we, instead of the ground truth labels, which were like these points, we use what we obtained from our solution, from this blue curve, and retrain. This time, the solution, the regression solution we get will be this orange curve, which is more similar to the ground truth curve. And if you continue doing self-distillation, it looks smoother, but also the function itself kind of moving towards zero function. But the point I want to make is that before the function collapses to zero, you already see a function like this orange curve, which looks very similar to the original function. So this is the regularization effect that you get if you do self-distillation. And here you see the evolution of these diagonal entries that I showed earlier, right? I was saying that, for example, based on the regularization operator, you get a D. Initially, it's dense. But as you basically train your model with the same training process, the D's that you obtain is evolving. So this is like, okay, the original D, this is like D raised to power 2, D raised to power 3, and so on. And you can see that the smaller eigenvalues here are shrinking faster. So already after one round of self-distillation, it's kind of like, okay, I only have 2 dominant, 3 are helping a little bit, but after like 4 rounds of distillation, it's like I only have 1 dominant and maybe 1 helping a little bit. So just continuously shrinking, the contribution of different eigenvalues, which means the contribution of those rotated labels, right? So it uses less and less components of that rotated label. All right, so I guess there are some details that in the interest of time, I'll skip. Actually, I think I'm already over time. Question and answer, but let this be the last slide. So this is now showing what happens with self-distillation if we apply to real data, real neural networks, and whether the observations we see there is consistent with what we obtained for this variational problem with L2 loss. Okay, first let's review what was the result. So what we showed was that with this self-distillation loop, you're actually under the hood, you are building a regularization. Is intensified in each round of self-distillation because it's associated with the power T, right? So if you do more and more rounds of self-distillation, it becomes more and more aggressive to kill the eigenvalues of that matrix that we showed, and therefore it uses less and less components of your rotated labels. So again, if you want to interpret this, it's a way of capacity control. So initially, maybe with a mild amount of regularization, you can benefit from this because it prevents you to overfit to your training data. But with any regularization, you can over-regularize, and if you over-regularize, at that point, it's going to produce poor models, very weak models. So you will not see a good performance on test data. But another point to make is that because this is a regularization, so if I look at the model that's, for example, obtained after a few rounds of self-distillation, its performance on training data should be worse, right? Because any regularized basically preventing us to overfit to the data, right? So it can fit less and less to our original training data. So it's expected that the training error increases, but the test error to decrease. But if we start to over-regularize, it increases again. And that's exactly what we see in these curves. So here we are using ResNet and BGG, and this is data with CIFAR 10 and CIFAR 100. And here you can see what happens after 10 rounds of self-distillation. We have test accuracy. So as I said, the train accuracy consistently goes down after each round of self-distillation because, again, it's consistent with the regularization story that we had. And here is the test accuracy. So you can see that after a few rounds of self-distillation, the test accuracy actually increases by a bit, but then you start to over-regularize. So after maybe about 6 rounds of self-distillation, it becomes very aggressive regularization, and your test performance. So this is what, if I'm not mistaken, let's see, the left 2 plots are on ResNet. Okay. Oh, sorry. The left 2 plots on CIFAR 10, both of them are ResNet here. The right 2 plots are CIFAR 100. So again, same trend. You can see that the training accuracy consistently goes down in each round of self-distillation. But the test accuracy can initially go high. Like maybe you get the peak at about 9. So this is showing that the theory that we obtained here to explain why in self-distillation we see a boost, the regularization result is consistent with what we see empirically with neural networks. As I said, there was this connection with wide neural networks in the talk. But with that, I end the talk to